So a consequence of being continuous is the fact that this theorem will hold. It's called the Intermediate Value Theorem. I'm going to give you the formal statement of it, but the picture is what you really need to get a good understanding of it. So here's the formal statement of it. All you need is for the function to be continuous on some closed interval. Whenever that's the case, the following will be true. Okay, so there'll be some A, there'll be some B. Those are X values. And then you go up and see the Y value, right? F of A and F of B. And what this says is, for all Y values in between F of A and F of B, this capital N value, as long as the F of A and F of A aren't the same thing, what the Intermediate Value Theorem says is that there exists a number in the X range, A to B, so that when you plug it into the function, you get that number out. That statement alone doesn't do it justice. What you really need is a picture. This is a picture from not our textbook, but from a different textbook. So I have an A, I have a B, which are X values. I have an F of A, I have an F of B. They aren't the same, they aren't equal. And I have a whole bunch of X values that are in between F of A and F of B. Call it capital N. That line there represents Y equals capital N. And what the Intermediate Value Theorem says is all the values of Y in between F of A and F of B, basically you're able to get to them. There's something in the X, there's a C value in the X that when you plug it into the function, you get that Y value out. It happens once. It could happen more than once. If you just lower that down, you'll see it happens multiple times. And so the Intermediate Value Theorem says that you're guaranteed that it's at least going to happen once. So it seems like, okay, what are you going to ever use this for? What's the purpose of this? But it's definitely a true statement. We don't have time to prove it, but all you need is the continuity. The continuity of the function is enough to guarantee. What does the continuity mean? The function isn't broken. As you start at that Y value and that X value, and you end at the other Y value and X value, and you draw a function that isn't broken, there's no way to do that. There's no way to draw a function that isn't broken and not be able to go through all the Y values in between. That's the heart of the Intermediate Value Theorem. All the intermediate values between F of A and F of B are attainable. You can get to them. You have to go through them. And sometimes you can go through them many times. The real reason why we care about this, though, is because it helps us to identify the existence of roots. The root of a function is where the function crosses the x-axis. So take this whole picture, basically, and push it down, where the capital N value is the 0, and it doesn't necessarily have to be that the F of A is below the F of B, or it could be the other way around. But if you start with the F of A being below the x-axis and the F of B being above the x-axis, then you have to go through the x-axis. Going through the x-axis, we end up caring about that. That's where the function has a root. That's where the function is equal to 0 at. And so we can use this theorem to at least know that there's an existence of a root. It doesn't tell me how I can find that root. It just says that I'm guaranteed that there is a root. If I have a Y value that's negative and then later on I have a Y value that's positive, as long as my function is continuous, I can't draw the graph of a function that does that and skip over the x-axis. I have to go through the x-axis. I have to have a root. And so it talks about the existence of roots. Let me try to take this and draw it. Let's see. No? Not going to work for me? Okay. All right, so I'm going to take this picture and just slide it down where basically here's A, here's B still, and F of A is down here somewhere. And F of B is up here somewhere. I can't draw a function that connects these 2 points and isn't broken and skips over the x-axis. Can't do it. That's the idea. That's the heart of it. That's why we really care about this. I can't draw a function that isn't broken and skip over that axis. I have to go through that axis. I can go through that axis multiple times. I know at least I have to go through it once, though, in order to get up there. And vice versa is too. I won't draw it, but if I start above and end below, I have to go through the x-axis. So that's why we care about it. Here's the formal statement of it. I'm not really particular about that. I'm not going to care whether you can state this. I want you to be able to use it. I want you to be able to apply it. And so the applying it is saying that, okay, since f of a is negative and f of b is positive, then somewhere in here, I know I have to go through the x. There's a root somewhere in that interval. And so those are the types of questions you'll see. Use the intermediate value theorem to show that there's a root of an equation. Now, I don't have a graph. I use the graph to help me help me explain the intermediate value theorem on the last slide. But now we're just going to be given the function. F of x equals this function, 2x cubed plus x squared plus 2. Some function, no graph, but I have an interval, -2 to -1, -2 to -1. The first question is, you shouldn't even be considering the intermediate value theorem if your function is not continuous. So the question at hand first is f continuous? This is f here. Is f continuous on this interval? And technically it has to be closed. And the answer to that question is, it's a polynomial. There's no place where you can't plug into a polynomial. The polynomial has a domain of all real numbers. So yes, it is continuous. Not just on that interval, on all real numbers. So, okay, so I can use the intermediate value theorem. All right? And intermediate value theorem says, okay, well, this guy is your A, and this guy is your B. So, go out and get f of A and f of B. Plug it in. What is f of -2? Be careful, there's lots of places to make a mistake. Replace your x's with -2's and use parentheses. I highly recommend it. Without the parentheses, you definitely could make a sign error. You can make a mistake. I want to take -2 and cube it. I want to take -2 and square it. And I want to see what that is. I don't really care what it equals, really. I care about what sign it is. That's what the intermediate value theorem cares about. Is it below or is it above? And so we plug that in, and do we get a negative value or a positive value? Negative. When you cube that -2, you get a -8. And so that's a -16. Yeah, you add 4 and you add 2. Not enough to make it not negative anymore. So it's less than 0. Great. Graphically, we are at -2 here. And I got something, I don't care what the sign is, but I don't care what the number is. I just know that I'm down here. Okay. Well, f of b, the other guy, which is -1. Do it all over again for -1. If all goes well, you should expect this thing to be positive, because otherwise we wouldn't be bothering with this intermediate value theorem, because we wouldn't be able to use it. You expect it to be positive, and it is. This guy gives you a -1, so altogether that's a -2 plus a 1 plus a 2. Yeah, it's positive, greater than 0. So somewhere here, and so we just take the following. F of A is less than 0. F of B is greater than 0. F is continuous on this interval. That's all we need. By the shorthand IVT. I don't know where, but somewhere in the interval, there is a C. There is something, x equals C, in the interval, so that when I plug that C in, I get exactly 0 out. There's a root. And you're done with that problem. Question on that? Is it clear? All right, good. All right, the second one here. It's a little. You know what? Let me change. I meant to change this. I'm sorry. Let me make this 0 to pi. Plugging 1 in, you'll be taking the sine of 1. We don't really know what the sine of 1 is, but pi. Let's do that. 0 to pi. Sorry, change the problem. Okay. Now, what's different about this one from the other one? Okay, there's trig, right? But just by the looks of it, though, one is set equal to 0 and one isn't. Okay. And we're trying to find out where the function is 0 at, so we need it set equal to 0. If it's not, just move the terms over to set it equal to 0. Either way, who you want to? I know it makes more sense to only move one term, but for some reason I want to move both of these guys over and call it 2 sine x minus 3 plus 2x. That's my function f. Do the same thing. A is 0, b is pi. Okay. What is f of a? Oh wait, I think I'm in trouble. I shouldn't use pi. I think I need to use measure. Oh no, I'm good. Yeah, 0 works. What is f of 0? 2 times the sine of 0, take away 3, plus 2 times 0. 2 times 0 is 0. What's the sine of 0? 0. All right, so this guy's negative 3, less than 0. Great. Okay, it won't always be that f of a is less than 0. It could be that the other guy is. As long as they disagree, that's fine. Okay, I think I set it up so that this next guy is positive. Let's see. If I plug in pi in, 2 times the sine of pi, take away 3, plus 2 times pi. Okay, but sine of pi is the same as the sine of 0. Also 0. Okay, so I have to understand that I am now looking at negative 3, but then plus 2 pi. I have to know how these guys relate to each other, who's bigger. Okay. And you have to know that pi is about 3.14. If you double 3.14, you'll be bigger than 3, so it'll be positive. Greater than 0. If it wasn't, you can do it. All right, great. And then this whole statement again that by the intermediate value theorem, by the intermediate value theorem, there's some c in that interval so that when you plug that c in, you get 0. So just make that statement again, and you're done. Okay? Finding what the c is, that's a whole different animal. And you would need a calculator, a computer, and that's not something we're going to do. Okay, 0 to pi, just parentheses, not equal to, with that f of c equals 0. Okay, problem with that is that 0 to pi, there's a bunch of numbers in there. It seems like it's a bigger interval than 0 to, than this guy up here, -1, -2 to -1. Okay, so that was officially the end of 2.5 of the intermediate value theorem. There are, I think, a couple questions on the next assignment that have you doing this. It doesn't scream at you, use the intermediate value theorem on this question, but hopefully you can figure out that they're asking you to use it. It isn't in the same format like this probably, where it says, telling you exactly what to do. But if they're talking about roots, chances are they're talking about the intermediate value theorem, for us at least, for now. Okay, and I'll change the animations to put pi in there and update the slides. All right, wonderful. Yeah. Bless you. Okay, so we're gonna jump quickly into 2.6 then. Oh wait, not that fast. So we're gonna not ready for that slide yet. All right. So what's different with 2.6? Now we're gonna let x go to infinity. Before we let the y value go to, we let the limit possibly be infinity. Now we're gonna let the x go to infinity. So what happens as x gets big, and then negative infinity? What happens as x gets small? And in actuality, what that means is we're going to end up finding what the horizontal asymptotes are. We know about vertical asymptotes. Those are the places where your function doesn't exist at. Now we're going to see these new asymptotes called horizontal asymptotes. So now x is going to infinity. But maybe possibly that it could be possible that you still have a limit, capital L. Or x goes to negative infinity, and you have some limit, capital M. Maybe L and M are actually the same. If that's the case, then there's a line, y equals L, or in this case, y equals M. that's a line, and your function is going to come up and asymptotically approach that line. Never quite get there, just sort of skim along it, maybe from above, maybe from below. It could happen. And we're going to look at different instances where that could happen at. Okay, here's an example of where it happens at in not the easiest example, but we had said back when we were looking at reviewing arctan that it has this graph where it goes on forever and it has a limit. I said one of the things that we definitely needed to know is that as x goes to infinity, it has a limit. As x goes to minus infinity, it has a limit. Usually these things aren't different numbers, but here in this function, they are different numbers. The capital L, the limit at infinity, is the pi over 2, and the limit at negative infinity is the negative pi over 2. And these guys are asymptotes. You come up and asymptotically approach that, you never quite get there. And that's what the graph of arctan looks like. All right, great. Other than that, we'll have some functions that are mostly either polynomial or rational functions. A polynomial divided by another polynomial, and we'll be asking the question, what happens as x gets big? Sometimes we'll have an easy answer, or we can just eyeball it and just know the answer right away. Other times I have to do a lot of work. And so let's just develop the framework so we can work through these problems. Here's just a question of combining what we did before with that idea of what we had on the last slide. Here's a graph of a function. Let me draw in some arrows here. Basically, wherever you see it, think that it continues to go on in that direction. If it goes off your viewing window, I don't want you to think it stops there. Okay, so I have this function called g of x. And the first question up is, what happens as x gets big? What does y go to? The answer is 2. Very good. That's your horizontal asymptote. Okay, great. Y equals 2 would be horizontal asymptote. B, what happens as x gets small? Negative infinity. Go to negative 2. Great. These other questions are back to the old, what happens at x equals negative 3? From one side, wait, I'm sorry, not negative 3, positive 3. What does that say? I'm sorry, that says positive 3. I blew that, I'm sorry. Positive, that's this guy right here, positive 3. X goes to 3. What happens to y? Both sides goes to infinity, so the answer is infinity. If one side went to infinity, the other guy didn't. It does not exist. All right, great. I think that's, no, at 0, both sides go down negative 3. But at, here we have negative 2 from the right-hand side. Negative infinity. All right, great. So they're different things. Whether x is going to infinity or the actual limit is infinity, they're two different things. I throw them all on one slide together so we can hopefully get them straight. And so anytime the function goes to infinity, then these end up as being the vertical asymptotes. We talked about those last time. Anytime when x is going to infinity and you get a number, these guys end up as horizontal asymptotes. Okay, a vertical line has equation x equals. So this one we get x equals 3 and x equals 0 and x equals negative 2. Horizontal lines have equation y equals. We'll get y equals 2 and y equals negative 2. These are the equations of the asymptotes. We're going to find out later there's a third asymptote. It's called a slant asymptote. It's an asymptote that has some slope to it. And but we're going to wait for that. I think our section 2.6 might have it in there, but I want to wait for it until we learn more. And so, yeah, that's the answer to these guys. Wonderful. All right, all those limit laws that we had before, okay, that was when you couldn't have infinity involved. Now, that was when x was going towards a, and the limits had to be finite. So all these are still going to hold. You just take, instead of x going towards a, x is going towards infinity. And so all these same limit laws hold. But see, when we had them before, it was about, okay, the collection of these limit laws allows us to be able just to plug in x equals a. But there's no just plug in x equals infinity. You can't plug in infinity. You can't treat infinity like a number. I mean, mentally you can think about a large number and try to reason what happens, but there's no plugging in infinity, like you can plug in x equals a. And so we still need to be able to tackle these limits and figure out what happens without the aid of a graph. And so here's an example, y equals 1 over x. That's what the graph looks like. So if I have a graph, I'm fine, but if I don't have a graph, that's what we're going to run into a problem. And of course, this thing does do this and this and this and this. So as x goes to infinity, y goes towards 0. As x goes to negative infinity, y also goes towards 0. This is the building block that we'll use. This particular function, 1 over x. Okay, any power of x in the denominator other than 1, the same action is going to happen. So if I look at 1 over x to the r, where r is any number that's a rational number, I'll still go to 0. Good. And then I need the thing to be defined, of course. I can't have something where I don't have the definition. But when I have negative infinity, I have to worry about raising negative numbers to powers that aren't, if I have a root, if r is a half, I'm going to have an issue here. So as long as things are defined, we can say this is true too. And so these are going to be the building blocks. The fact that 1 over x goes to 0, 1 over x to any power goes to 0. We are going to turn our problems algebraically to have multiple terms like this, some constant over x to a power. That's what we're going to do algebraically. If we have to do it algebraically, there will be three different situations that could happen. We're dealing with a function where we have a polynomial in the numerator and a polynomial in the denominator. It's called a rational function. Okay, there's 3 different things that could happen. You could have what we have going on here. When you have a polynomial, the degree of the polynomial is something that's important, and both of these have the same degree. Both of these are degree 2. If you have a limit that's going to infinity, and the degree of the numerator equals the degree of the denominator, you can eyeball what the answer is. There's no math calculation you have to do at all. These other terms don't matter, right? 4, who cares about 4 as x gets big? The negative 8 on the bottom. No one cares about that as x gets big. The negative x, that gets big too, but it gets dwarfed by the x squared terms. Those are the guys who really matter. And so because those guys don't matter, this function behaves exactly like 3x squared over 2x squared. And so we can eyeball the answer and say 3/2. Okay? Here's the algebra way of doing it. I don't want you to have to go to this. I need you to learn this way because we won't always have that shortcut. They won't always be equal to each other like this. When they are equal, you can definitely do the shortcut. I'll put the shortcut at the bottom. I said it, but I'll put it at the bottom. But here's the algebraic way of solving these problems. Remember I said it, our goal was to turn this into have many terms that look like what we had on the last slide. So I need to find first the highest power that's in the denominator. The highest power on x. In this case is x squared. And p is 2. And I'm going to multiply by the reciprocal of that. Both numerator and denominator, I'm going to multiply by 1 over x to the p. What that's going to do is give me those terms I don't care about, the terms that didn't matter to me, they'll end up looking like something over x to the p, and they'll go to 0. And I can legitimately say I don't care about them because they're going to 0. And so when I do that and distribute it across, it really shows that the first terms are the guys that matter. This is why that shortcut works. I don't want to give you a shortcut without telling you why it works. And so when you distribute that across, those terms that I wanted just to throw out, it's okay. It's reasonable for me to say that because they're all going to 0. They're all of the flavor that was on the last slide, 1 over x to some power, or constant over x to some power. They all go to 0. X gets big, right? X gets big. 1 over something that's very big is very small. That's going to go to 0. 4 over something that's very big, very small, goes to 0. 5 over something that's very big goes to 0. Negative 8 over something that's very big goes to... All those guys don't matter. They really don't matter. And so they all go to 0. All I care about is these two guys, and I get 3/2. Okay? I don't want you to have to go through that. I just want you to know why the shortcut works. Here's the shortcut at the bottom. If your degree of your numerator is equal to the degree of your denominator, then just focus on their coefficients. When I say leading term, I don't mean the one that's first. These things can be ordered in any order I want. Leading term means the highest power term. So I want you to use this shortcut. I want you to eyeball it. Just give the answer. Move on. I'm okay with that. Okay? But you need to see this because in one of our 3 different versions of this type of problem, we're going to need that. We have a shortcut for the second version as well. The second version is when the degree of your denominator is more than the degree of your numerator. You can easily just say what the answer is. Let's go to that. Here's an example of that. X to the 4, x squared plus 4 in the numerator. X, and it doesn't matter, plus or minus. I'm sorry. Did I gloss right over that? Doesn't matter, plus or minus for that shortcut. Either way, all those guys are still going to 0 because the denominators are blowing up. Blowing up small, blowing up to negative infinity or blowing up to positive infinity. They're all blowing up. Okay. All right. So this time it looks like they're the same, right? They're right in front. X squared, x squared. Looks like they're the same, but no. There's this guy that's hiding from you. That's the leading power. So the degree of the numerator is more than the degree of the denominator. I'll show the shortcut on the bottom. Simply, the answer is 0. Okay. No coefficient, nothing. 0 is the answer. In every case where the degree of the numerator is more than the degree of the denominator. Okay? But I'm going to take you through the algebra to show you why. And because we need to know the algebra for the third type. And so find the leading term, x cubed, multiply by its reciprocal, distribute that across. And you end up not caring about anything that's in the numerator. They all go to 0. 2 of your 3 terms from the denominator go to 0. So you use the denominator so that you force it to go to a constant. And so I could probably set it up where I use the highest term in the numerator, but you really want the highest term in the denominator so that you can force the denominator to go to a constant, and then all the actions happen in the numerator. Either it's going to be that same constant, or it's going to be 0, or we're going to see that it could be infinity. So all these guys go to 0, and the answer is 0. The shortcut is that if the degree of your numerator is more than the degree, I'm reading it backwards, sorry. But yeah, if your numerator is less than your denominator in degree, then the answer is just 0. And once again, I don't want to gloss over it this time. Doesn't matter whether you're going to plus or minus infinity. So use the shortcut in those 2 instances. You don't have to go through all the algebra. Know the algebra because the third version of it, when the degree of the numerator is less than the degree of the denominator, then you need the algebra. There's no way to say exactly what the answer is. Okay. At least you know that it's either infinity or negative infinity, but we can't nail down which one it is without going through the whole algebraic approach. So here's that example. My numerator degree is 3. My denominator degree is 2. My numerator has a higher degree than my denominator. Okay, it could be infinity, it could be negative infinity. But there's no clues in the problem right away that we can nail it down. It depends on 3 different things. Okay, but let's do the algebra and I'll tell you what those 3 different things are. So what's the algebra? Go to the highest term that's in the denominator. Don't worry about the coefficient on it, just the term, and multiply by the reciprocal of that term. Distribute that across. So we'll have the 1 over x squared to distribute across. What does that give you? So it leaves you with an x in the numerator. Yeah, those terms don't matter. And so what it leaves you with is x over a negative 2. So there's lots of factors that play a role. There's 3 factors that play a role. The negative 2 in the denominator, the fact that it's negative. So the coefficients that our surviving terms have, that matters. whether I'm going to plus or minus infinity is going to make a difference, and the power on x is going to make a difference. The surviving power of x, right now it's just a 1, but that's going to all play a role. This function will behave like x over negative 2 as x gets big. So you can't plug in infinity, but the bottom stays at negative 2 while the top gets very large. The result is negative and large, right? Negative infinity. Right? If I take a huge number, a billion, I don't know, whatever a huge number is to you, and I divide it by negative 2, I'll have negative half of a billion. Negative is small. Okay. So anyway, it goes to negative infinity. So the answer is either positive infinity or negative infinity. If you want, you can flip a coin. You won't get credit for flipping the coin, but you have a 50-50 chance of getting the answer right in this situation. So how do you know what it is? You have to weigh those 3 factors. So your degree of your numerator is more than the degree of your denominator. Okay, it could be plus or minus infinity. Here are the 3 factors. The coefficients that were surviving. Positive 1 in the numerator, negative 2 in the, it matters. Okay, if I'm gonna do the same problem. I'm going to change it. I'm going to change some different things about it. It's going to flip it from negative infinity to positive infinity. Okay? So deleting, if I was to make, right, if I was to make this coefficient be negative 7, simply by putting a negative 7 instead of a 1 as that coefficient, I know it looks like a 1. If I was to put a negative 7 there, then this would be negative 7, and my answer would be positive infinity. So that little guy matters. The leading coefficients matter. Leading being the surviving guys after the canceling. Okay. The leftover power on x matters. It doesn't matter right here as I'm going towards infinity, but what if I was going towards negative infinity? Okay, back to the original problem. Sorry, let me erase my sloppy negative 7s. Back to the original problem. And let's go right to the version of it where we have limit x goes to now negative infinity of x over negative 2. Now it's negative in the numerator and negative in the denominator. So it's going to go to positive infinity. So that matters. Okay. Now, what if the power was squared? What if the leftover power, what if this x thing was squared? What if the x was squared and I had a negative 2 and I don't know, I'm going towards negative infinity. I'm sorry, I think what I just did there was the third one. Yeah, Okay, this is the C option here, the change on this. If it's negative 7x over negative 2 as x goes big, that is the that's the A option. Here's the B option, sorry. Okay, say I'm going towards negative infinity, but I'm now squaring that. It's no longer negative anymore like it was here. The top is now positive while the bottom is negative. So they all play a role, and so you can't just say exactly what the answer is without weighing all 3, and you have to do the algebra. Okay? There's no way to say it right away. I want you to show me the algebra, show me the canceling out terms, show me what survives. I'm sure that you can just, cross things out. I don't want that, though. I want to see this algebra in this particular instant when the degree of the numerator is more than the degree of the denominator. Okay? I don't want to see it in those other instances. I just want you to give me the answer. Make sense? Okay, so making small changes will affect the answer. Okay, great. Oh, we're not ready for that one yet. How are we doing on time? Let's see. Yeah, 10 minutes. Yeah, we can't do that one in the 10 minutes. What's this one here? Yeah, okay, I'm going to have to hold off on this one here. Let's try this one. I think we can get this one done. Okay, so the issue is, it's not always going to be Polynomial divided by another polynomial. It's not always going to be like this. It'd be nice if these are the only kinds of problems we had when we're trying to consider limits at infinity. That would be wonderful. But it's not always the case. As soon as you throw one square root in around the polynomial, then you can't do that same idea of what we're doing. There's no shortcuts there. Okay? And so here's two examples. We don't have time for this one. This one is very involved. We'll start with this one on Monday. But we do have time for this one. Let's see if we can do this one. Okay, x is getting big. You would think that the first part is getting big, right? Something big. I can't plug in infinity, but something big squared times 9 plus another something big, and the square root of that big is still kind of big, right? And you're subtracting something which is also big, minus 3 times something big. You would think that it's big minus big, but there's different degrees about big. You can't just say it's 0. Okay? It's not infinity minus infinity. Okay? So we have to do something to it. All right? And the thing is, it's not a fraction, right? Okay, we're going to have to just put it over 1. And the conjugate. When you see roots over, roots involved in a limit, think about the conjugate is what? Take the same thing on the left and right, but change the sign in between. So I need a fraction, though, because I can't just multiply by a conjugate without dividing by the same thing. I need to not change my limit. So I'm going to multiply top and bottom by the conjugate. Same thing, but different sign in between. Not underneath. The in-between sign changes. I try to emphasize it by making it red. Okay? And we're going to FOIL out the numerator with the goal in mind of hopefully getting rid of roots. Okay? When we FOIL out the numerator, what do we get? Oh, wait, I'm sorry. Wait. Oh, here it is. Okay, good. Right? Root of the times itself, we just get what's underneath. But then the middle terms will cancel. It'll be minus 3x root plus 3x root. We don't care about those. It's set up so we don't care about those. And then the last terms, that's a negative 9x squared. So that's convenient. You have 9x squared plus x, and then a minus 9x squared. They cancel. All right, the denominator still is what the conjugate was. Nothing you can do to that. Leave it like that. And your numerator is now x. Okay, so it's not a polynomial, but it's getting better for us. We're able to find our way through this problem now that we have this fraction. It's not rational, but we can kind of reason out what's going to happen here. Okay. To show what's going to happen, unfortunately, we need the algebra. But we can reason out what's going to happen. Who cares about x, really? This x that's down here? Who really cares about that? As x gets big, this guy's going to be the dominating term. This one won't play a role. And so when this one's not here anymore, when this one doesn't play a role, basically you're just looking at the root of 9x squared, which is 3x. And here's another 3x added to that, 6x. If your numerator is x, your denominator is 6x, x is canceled, the answer should be a sixth. We can reason that, we have to show some work though. Okay, I want you to use that as like the back of the book answer. The answer is a sixth, just by using the logic that this isn't going to matter, and then you'll reason out what happens after that. But to show it, we have to do the same kind of, who's the biggest term in the denominator? And you would think it's this x squared, right? 9x squared is the highest power on x, right? But it's under a root. So it's really not an x squared. It behaves like an x. So the highest power in the numerator is x to the first, and the highest power in the denominator is also x to the first. So we're going to multiply top and bottom by the reciprocal of that, 1 over x to the first. That's the algebra, right? Find the highest power in the denominator and multiply by its reciprocal. Okay? It's x to the 1 this time. So 1 over x. What does that do for us? It changes our numerator to a 1. But what it does to our denominator, we have to do some work. Okay? So our denominator, right? Yeah, it's fine. Yeah, 3x times 1 over x, that's definitely a 3. 1 over x times x, that's definitely a 1. But this is an issue. Root 9x squared plus x all over x. I don't know right away. It'd be nice if it also had a root. X, if it had a root. And so I'm going to make it have a root. I'm going to make it interact with that. Right now, I can't do this. I want to cancel so bad, but I can't. Don't you want to cancel that? It's under the root, though. You can't. So here's what you do. You make this guy have a root. Right? X is the root of x squared. So make it have a root. Just change its name. It's the same thing. You just gave it a different looking name. It really is the same, though, because you want them to interact. And now that they both have a root, now they can interact. Okay? And you get the cancellation that you want. I'm sorry, that was out of order there. That should have been one of the things that we were talking about right here. My animation's out of order there. Okay? So now they're both underneath the same root. And now I could do my cancellation, but still, don't just cancel this. This x squared is underneath both of these guys. Think about it as like 9x squared over x squared, yes, but also x over x squared. You know what I mean? Still underneath a root. So yes, it is 9, but then this guy is a 1 over x. And remember, that's the guy that I attacked at the beginning and said, I don't care about that guy because it goes to 0. And the root of 9 is 3, and 3 plus 3 is 6, and 1 over 6 is 1/6. Have a good weekend. Come back on Monday. Don't be scared away.